morning, friends and partners. Thank you for joining this session. I would like to extend my warm welcome to you all. And also thank you, Güntner, for organizing this very good platform. So all of us key leaders here in the industries are able to share our ideas and technologies. So today my topics will be about heat pump. I'll be sharing some energy saving solution from our heat pump from both cooling and heating perspective. And of course, how do we apply heat pump in general? Hopefully, throughout this session, you will get some common understanding about how we can progress of heating to a sustainable journey. So a little bit of Johnson Controls. Ever since Warren Johnson founded Johnson Controls about 140 years ago, which is our founders, we have actually acquired, developed industries side by side, strength to strength. And today, we have a huge amount of industries that we covered, from HVAC chillers, industrial refrigeration, where I'm coming from, building automation and controls, security, fire detections, and many other industries. And of course, we carry multiple product brands, just like Güntner, and we work together at Güntner in many projects in terms of cooling, and of course, towards heating as well. And all this, basically, overarching design of our systems, right, is to achieve three very basic objectives. First of all, is to develop, to enhance a smart building technologies through efficiency, electrification of the system, and of course, digitalizations. As you all know, that digitalization is today becoming more and more important towards the data gathering and analysis of the buildings. And of course, we also want to achieve a more healthy, enhanced experience of the well-being of the people staying in the building, whether it's factories, industrials, even data centers that we are going forward today. And most important of all is to achieve sustainability. And this keyword has been highlighted over the last few speakers, that our world is going to be sustainable. Otherwise, we will face consequences as the global warming grows towards more serious consequences. So with this sustainability concept, my starting definitions is for a heat pump. Right? So what basically is a heat pump? As all of you know in the audience, maybe some of you have already known heat pump for a long time. Some maybe just know a little bit. Basically, heat pumps are designed to produce hot waters at a specific temperatures, and heat is extracted from a low temperature heat source, right? Any waste heat that you have from air, ground, condensers, ground waters, and so on, and going through the cycle of refrigeration cycle to develop heating applications on the heat sink side. So that is a very basic understanding of heat pump, right? So why do we do heat pump? Right? As we have explained earlier and the few last speakers, sustainability is one of the key messages. So one of the economic benefits of heat pump is to save energy costs, fuel costs, as we produce heating versus boiler fuels, which I will explain a bit later about the differences. And of course, with the saving of cost of the fuel, we'll be able to achieve environmental benefits by reducing carbon footprint, by reducing global warming initiative, of course, reducing water consumption if you are tapping into waste heat source from cooling towers or condensers. And the third, of course, in many of the companies that's going towards a net zero journey in the next 20, 30 years, these company regulations, sustainability programs is an important step where heat pump can help to do a low carbon energy saving and cooling at the same time. So, I just want to highlight a bit of the differences between the chillers and the heat pump. I think most of you will know that the chillers basically function is to chill water from 12.6 as an example, and of course reject heat through the cooling towers. So most of this heat are being rejected, should I say. So this is the very first basic definition of a chillers. As we evolve, sometimes the waste heat may be recovered. We call it a heat recovery process. But still, in these two concepts here, our primary controls is still on the chill water side. Whereas anything on the heat rejection, it could be wasted, it could be recovered. Primary controls point lies on the chillers. And the third is where the heat pump concept comes in. When the controls start to shift towards high temperature heating controls, which is where you want to achieve 60 to 90, for example, as in this particular case, and free cooling from the cooling side, then it becomes a real definition of a heat pump. And of course, by doing all kinds of lift from a low temperature to high temperatures. It could have a lower lift scenario, where let's say you are using cooling water at 30 to create hot water up to 90, or it could be up to 6 degrees chill water and up to 90. So that will be more on high lift configurations. Now, about heat pump, definition of heat pump, as we say, the COP of heat pump is important for us to understand. Just let me go back a bit. Yep. How do we define the COP heat pump? I think most of you are very, very familiar of COP or refrigeration system, right? Basically, you have an input of energy, cooling energy, with the input of power. So in this particular scenario, you can see that 5 units of cooling divided by 1 basically give you a COP of 5. Very simple understanding. And through this whole cycle of heat recovery, heat rejections, you find that 6 units of heat is being generated. And if you use that over the power of 1, you basically get 6. So that is a very relative terms of COP measurement. But what is more important is that if you harness the power, the energy of both cooling and heating at the same time, basically you get a lot more out of that, which is 11 in this particular case. So that is a very important combined concept of heating and cooling to achieve a much more efficient system than just cooling alone and let the heat be wasted. So, compared to the boiler, traditional boilers, we know that the boiler has only one direction, which is from pure heating, injection of fuel, going towards process heating, for which the efficiency of boiler is always less than 1, maybe sometimes even 0.8 to 0.7, right? So a huge amount of heat is being produced, fuel is to be used just to get the same amount of heat. Whereas in the case of a heat pump, you will see that any of the waste heat that has been produced by the factory or by the building, hopefully can all be recovered, right? And with a little bit injection of power, we should be able to generate the same amount of heat which a boiler is going to generate. So out of this, you can see the COP of the system here with the heat recovery concept is definitely more than 4 or 5, some even higher compared to the boiler. And in this aspect, saving a cost of fuel, right? And using a little bit of electric power, you'll be able to get a much better payback compared to just a one-way track of heating, right? Of course, there are many other benefits for a heat pump versus boiler. And of course, you have fuel saving, you have less carbon emission, you have lesser footprint. You may have a little bit of a maintenance cost to maintain the system, but in the life cycle cost of the entire heat pump system versus the boiler, the equation definitely shifts towards the usage of heat pump. Now, just to give you a snapshot of the energy cost differences consumption, in particular case, I'm taking Indonesia in general. You can find some of these energy rates and so on from the website. And a very quick comparison, right, shows that in general trend, diesel fuel oil and electric are one of the most higher energy consumption costs in running, let's say, powering 1,000 kilowatt per hour of energy. Now, natural gas seems to be a very useful form, a very cheap form of power, and that's why a lot of boilers today in Indonesia are powered by natural gas. Of course, some of them are shifting towards biomass, but if you still compare that, a COP of 4 to 6 of a heat pump on the other side, right, with the efficiency of heat pump, you basically lower your electric power consumption, and with the high COP of this heat recovery, you basically lower your cost of operations. And of course, we know that the great emission factor in Indonesia is being powered by coal power plant in majority of the cases. Yes, it has a large CO2 emission, but through that of a heat pump, you actually reduce the carbon content of the emission. So that is a very good representation of why a high COP machine delivers lower power of energy consumption, delivers lower carbon footprint throughout our journey towards sustainability. Now, just to illustrate a bit of how this heat pump is being applied across industries, for those of you who knows very well a system like this, where it is a ammonia centralized plant. So we actually capture the waste heat from the hot gas discharge of the system. From the hot gas discharge, we can actually go through a heat pump cycle to generate hot waters. In this particular case, maybe about 60 to 90 degrees. And of course, that is one way where heat pump can be integrated into the system. The other way is a very similar chilled water system you have with common cooling towers, where you actually tap a cooling water source from your cooling tower and transfer that into a heat source for you and into hot water through the cycle of a heat pump. So both scenarios are actually doing what we call a heat recovery, achieving high water temperatures using this heat recovery through the heat pump. In general, if you use an ammonia heat pump, you have a COP of 4 minimum or even higher. So that gives you a lot of cost saving, a lot of carbon emission saving at the same time. And there are also integration, right, of heat pump through a general chilled water system, where you can see here there could be two ways of integration. One of them is what we call a secondary pre-cooling concept, where this waste heat, this chilled water system will pass through a heat pump where it's being pre-cooled, and then you can generate hot waters on one side and saving energy on the existing chillers, running lower part load energy. So there's a lot of saving on both sides, the heating side from the boiler and the cooling side from the existing plant. And of course, sometimes you may want to integrate heat pump as part of a chillers program where it will combine with your existing chillers to deliver a total chilling solutions, but at the same time, recover the energy from the heat pump to generate hot waters. And if you have a lack of waste heat source, for example, if you don't have much cooling waters or you don't have much condensers, then another way to tap is the air. Air source heat pump is also getting popular in commercial products where hotels and so on need these products. But in industrial cases, we could also adapt that with, let's say, a simple air cooling unit. We have partnered with Güntner for several projects proposal using this as a heat recovery. And through this cooling process, you can gain high energy heat on the other side to do your process heating. So that is one way where we could actually integrate this in a very useful manner. And of course, air source heat pumps are much more efficient for a hot country, a warm country like Indonesia, compared to a cold country, basically because of the lift that you have to generate the powers. Now, a little bit of the portfolios that we are developing. My purpose is not to show a lot of Johnson Controls product. That is a step going towards a journey of more and more higher development towards steam heat pump, right, ultimately. So the journey progress for some of our products with different refrigerant, right, starts from a very standard temperatures, maybe about 50, 60, and this product has been exist for the last 20 years. But today, as the journey towards higher temperature heating, lesser boiler fuel consumption, we are going towards higher and higher temperature heat pump. And through this journey of high temperature heat pump, you see that the evolution of the refrigerant type is to be evolved, is to be used. And we are also developing different compressor machines to handle higher pressures, high compression in order to deliver hot water temperatures. And you can see when you go up to about 80 to 90, ammonia is to be a popular heat pump. And of course, we also in parallel develop products which are more competitive in the case of HFO heat pump to address customers' concerns about cost. And we also have high temperature heat pump up to 120 or even more in future, where we use water, ammonia, and also some absorption cycles. And even hydrocarbon are today being featured towards high temperature heat pump. So this is just a very quick run-through where these are the standard commercial products from air side, air to water, and water to water using different HFO, HFC refrigerant to achieve high temperature heat pump, probably to the range of 80 degrees C. For higher temperatures, as I mentioned before, Johnson Controls, especially with the development of Sabro in Denmark, have come up with a series of ammonia heat pump, starting from single-stage compressor and dual-stage compressor to do two different types of staging, high lift to achieve about 95 degrees hot waters, even high-capacity screw heat pump. But the more interesting is we are developing into what we call higher temperature, high pressurized water heat pump, where we can achieve 110 degrees with a combination of ammonia and water, and of course, with the use of hydrocarbon to achieve even higher hot water temperatures. And not forget that for those of you who are in the power industries, I heard about CCHP concept yesterday during dinners. We have absorption chillers that can capture waste heat and transform that into chill water. And of course, we could also parallel using absorption heat pump in this case, where the absorber with the mixtures of lithium bromide and water as a refrigerant is able to deliver high temperature heat output, and for which we are able to deliver this kind of high temperature heat pump, absorption heat pump, without any compressors, with the driving force of a waste heat source to deliver this application. And the future to come, right, as I show you, this is a kind of in development progress, that as we move towards higher and higher temperature, targeting to replace boilers in the near future, we are going towards a steam heat pump. And this journey is not easy. And as we speak, as we develop, we are going through a basic cycle of hot water generation first, just like any hot water heat pump that we have. When it reaches up to 100 degrees C, we could actually flash into a separators, a flash tank. And we will then go through a mechanical vapor recompression cycle, which is typically a centrifugal compressors, which will be able to pass the steam at a saturated pressure, stepping it up multi-stage to higher pressure to produce steam at the end, hot temperature steam, high pressure steam, to achieve the final objective of getting rid of boilers. So that is the journey of our evolutions of heat pump. I'm sure in many other competitors' view, many ways and innovation has been going on to really stress the development of high temperature heat pump. Now, heat pump products, it's sometimes say plug and play, but I would say it might not be the case. As we learn through many experiences, learn through many projects that we executed, energy audit and energy studies are mapping a heat source and a heat sink with the right solutions is very important, right? By going through a heat pump energy audit studies, we go to the customer sites, we go to several visits of engagement with customers to understand, right, where is the heat source coming from, where is the heat sink is going to be delivered, what kind of flow, what kind of temperatures we're talking about, what fluctuations of that, how do we match when no heating is required, how do you reject heat, how do you get enough heat from the heat source to produce the right amount of hot water. All these are being studied as we journey through the customers and give the right proposal so that customer can really benefit from this instead of just doing a fairly simple solutions without much thought. So heat pump basically, it's going to be not an easy journey, but definitely it is worthwhile at the end because some customers will see the benefits of energy savings, the benefits of carbon saving. Now, I just want to cover the few projects highlight that we have gone through. Right, there are three projects we have done over the last 3 to 4 years. Brewery plant projects in Vietnam, ice cream plant projects in Thailand, and of course, near East Java, we have a yeast production plant that is being recently secured with a heat pump. And of course, heat pump can also be potentially applied and used throughout many other industries where parallel cooling and heating are being used at the same time. So from dairy, breweries, and many others. And in fact, today, over the last 6 months, we see a lot of hotels across Singapore, even Southeast Asia, are going into heat pump, commercial heat pump applications. So this is one highlight of the projects in Vietnam based in Vũng Tàu area. For some of those Vietnamese, you might be familiar with this area. And this customer is actually undergoing some decarbonization journey. So they've done a lot of scope 1, scope 2, even scope 3 of the decarbonization. And they're finding ways to even reduce more heat pump, more carbon emission by, say, engaging Johnson Controls to study how do we reduce more of the energy cost saving. So we have come up with a solution where the ammonia condensers is a potential heat source because in brewery plant, many of this cooling is done through a centralized ammonia plant. So with that, we actually put in a water-cooled condensers in parallel to these evaporative condensers so that the normal operations, right, all the heat will be rejected by the PHEs, and we will then deliver that to a heat pump cooling cycle and produce hot waters at about 73 to 85. So the evap condensers will be at standby in this case, right? In case there's a need to service, then the condenser will start to kick in again, right? So these particular projects help the customers to save about 15% overall cost of energy consumption through the use of a 4.0 COP heat pump and it saves approximately 160 tons. It doesn't sound a lot because these customers has already been using biomass boilers through their project. So we are saving some of the fans, cooling towers, and many other subsidiary equipment. This is the pictures of how the installation looks. So we have the PHEs on top of the building roof where the condensers are used. And then we have the machine rooms, and of course, controls and so on are being supplied, installed according to a specification of these customers. And of course, we have a parallel project in Thailand, ice cream production plant, where actually they are looking for ways to reduce that. These customers has been using hydroelectric power for most of the entire plant, except the use of one boiler, which is still there. So they wanted to really decarbonize the whole journey together by the use of heat pump so that we can get rid of that boiler in one shot. So we tap the waste heat source from our cooling of the compressors. For those of you who are doing ammonia refrigeration system, you know ammonia screw compressors need some sort of a cooling on the oil side. So with that, we actually use this heat pump to cool the oil, extract the energy, and produce hot waters on the other side. So this is one very good example where we tap that into an ice cream plant production for both parallel cooling and heating. And the customer save approximately close to 30% of the energy cost with a COP of 4.6 for the heat pump and almost close to 800 tons of CO2 emission reduction. This is how it looks like. So our project guys are fine-tuning the heat pump as we go through the installation phase. And of course, these customers has insisted that we make sure that the whole entire heat pump project is captured, energy data are being used and formalized, and actually control loops are being put in place to make sure that this heat pump works pretty well when the heating demands start to kick in. Right? Now, another highlight project which I just want to share, it's in Malang, which is in Indonesia. So this is a yeast production plant. It's a French company. So basically, in this yeast production process, spray drying is one of the key applications for heating and cooling to produce hot air that goes into the chamber, all right, to heat up. So you need to heat, let's say, the air from about 30 plus degrees C all the way to about 25 degrees C. At the same time, dehumidify the air. So instead of using steam to heat up one of the steam coil, we're going to use hot waters. And that's where this hot water heat pump will be very useful for these particular companies. And of course, as we journey through together with this company, they will probably project it to save about 40% of the energy cost with a high COP heat pump being developed, customized, dual stage heat pump, and the potential saving of CO2 is tremendous for this company. Just to give you some highlights of the projects that we've installed. So we have 2 parallel heat pumps together, one future in the near future for the next phase of the project, going through a hot bottle tank. So that's part of the journey to actually looking at the load profile of the heating and deliver that hot water temperatures into the spray drying steam coil. Right? In parallel to these projects, right, besides the driving force of our dual pack, which is the ammonia heat pump, we have also delivered York chillers to do spray drying cooling process for the coil, which I think heat to the cooling tower to be recovered to the heat pump. And also we also have a York Hitachi absorption chillers to produce chill water while capturing waste heat from some of their biomass boilers. Now, one of my last key projects is a still case study where we are still doing some project heat pump mapping analysis with the customers. We are actually partnering with Güntner. So this customer requires a pre-ambient air temperature heating to about 120 degrees C. Before that, we would like to recover energy from that of the cooling towers to produce heating for the heat pump so that the air coil from what we call an air coil product from Güntner is able to deliver that heating across before it finally goes up to the plant. So in this particular case, while we've done analysis of these customers, we have quite a huge amount of potential saving for the customers with a high COP heat pump and, of course, a huge amount of CO2 as well. So with that, I'd like to thank you, all of you, partners and friends, listen to me about these heat pump sessions. I really appreciate your time. And we meet together in the same table. It's our key members here with help, of course, towards heat pump presentations. We have Louis, we have Eric, who is our sales leaders, and of course, our local sales representation. So feel free to engage during these sessions. Any questions, I believe we will be glad to help to answer, help to clarify, and enjoy yourself to the sessions. And I thank you.
Thank you very much, Pat Chow. We'll let you back to your seat. Thank you so much for...